This is actually a continuation of the central limit theorem. It's distribution of the sample mean. With the mean and the standard deviation, we bet on individuals. With the mean and the standard error of the mean, we bet on the average. Not only are we betting on the average, we're betting on the average of averages, which we don't actually have. So the main thing that we have is the standard error of the mean, which is the standard deviation divided by the square root of the sample size. That's what our bets are based on. We are using normal distribution probabilities from the central limit theorem, and we're using the standard error of the mean as the distance measurement. Distances for the average are based on the standard error of the mean. If we have a population and we draw a sample of 1,000, or we draw a sample of 10, we aren't going to get a different standard deviation. We're just going to estimate it, so that the real kick comes in the standard error of the mean, where we divide by the square root of the sample size. So we need as big a sample as we can get, but after a while, more samples don't get us anything, because this is only the square root of the sample size. Right, in here, in MyOpenMath, there's a file, sample mean and intervals. So go to MyOpenMath, and we want to download that file. And the tab we want is Samples. And this is a sample of size 10 and a sample of size 100, and they're from the same normal population, a mean of 100 and a standard deviation of 15. And all we're going to do here is get the average for each of these samples. And there's a spot for the average. We want equals AVER, and average comes up, and you can spell it out or double click it, and we just want the average of that range of numbers. And the average is 100.7. Right, the population average is 100, the real population average, so we're pretty close. What this is that we don't usually get, we know the real population average is 100 because I made it that. Usually, or almost always, you're not going to know what the population average really is. We've got an estimate, and that's the best we can do. All of this is a bet. Here, I don't have to bet because I made it up. Usually, you don't know the bet. You're betting, and you don't know the real case. All right, next thing is the standard deviation. And for this one, I'm going to use stdev.s. And on here, in Excel, it has a .s and a .p. The p assumes that we have a population, and we don't. We always have a sample, so I'll always use .s. And the only difference between these two is the divisor. The .p uses a divisor of n. The .s uses a divisor of n minus 1. So for anything bigger than 25 or 30, there's no distinction between these two. But we actually have a sample, so we're using .s, mark it, and the estimate of the population standard deviation is 14.05 from this one. And I'm going to knock decimals off. The standard error of the mean is the 14.05 divided by the square root of 10. That's our sample size. So take that equals 1405, whatever's in that cell, divide it by SQRT 10. And we get 4.4. This is the difference between our bet on an individual and our bet on the average. If we bet on an individual, it's 100.7 plus and minus 14 to get a 68% bet. Betting on averages, we have 100.7 plus and minus 4.4, which is a whole different deal. So we go from a really wide bet on an individual to a good bet on the average. Right, then these values here get the average and subtract 2 standard errors, then 1 standard error, add 1 standard error, and add 2 standard errors, equals the average minus 2 times that standard error of the mean. Then the average minus 1 standard error. That's a truly heroic number. I'm going to make all of these 1 decimal. There's no point in doing more. The average plus 1 standard error and plus 2 standard errors. Average plus so here's my bet. The real population mean is between 91.8 and 109.6, 2 down and 2 up with 95% odds. So my bet is 95% that that interval contains the true mean. In this case, I know it does because I made it up. The bet that the average is between 96.3 and 105.1 is 68%. Then do the same thing for the sample of size 50. Average, standard error, all the rest. The average is 101.3. The standard deviation is 17.24. Even though I had a sample size of 50, I still get basically the same standard deviation. It was 14 with 10 observations, it's 17 with 50, and it's pure luck, just the way it came out. The standard error of the mean is the standard deviation, 17.24, divided by the square root of 50. And we went from 4.44 to 2.44. That's the gain we got with a sample size of 50. This is the only control there is in statistics outside of experiments. If we're doing samples and estimates, the best thing we can do is get more samples. The problem with get more samples is each one costs the same or more. Right, we're doing a sample in a production facility. We're testing ball bearings. We take a ball bearing out, we've got to measure it and get the width. We take another ball bearing out, we measure it, get the width. The first one gives us as much information as possible. The second one gives us 1 over the square root of 2 times as much information. As we go along, by the time we get to 100 ball bearings, each one costs the same to measure. But the return in information is 1/10 of what we got from the first one. So more samples are better, but they are decreasing in value. Minus 2 standard errors is the average, minus 2 times the 2.44, minus 1 standard error, plus 1 standard error, and 2 standard errors is 106. Look at the range of the bets. From 10 samples, we go 91.8 to 109. For 50 samples, it's 96 to 106. We've squeezed it down that much. Look at the standard error compared to the average. For the 10, pick a spot, and we want standard error 4.44 divided by the average. And as a percentage, I'm going to convert that to a percent, and you can do it by multiplying by 100, or just go to that spot, make sure that cell is marked, and then click percent up on the top in the format box. 4.4%. Look at the let's start with 2 standard errors down. The 91.8. Instead of a 91.8, I'm going to make it as a percent of the average, so that this 2 standard errors down is twice this 4.4. So that here, this is minus 8.8% of the average. It's 2 standard errors down. The standard error is 4.4% of the average, so that this one is twice that number down. And it's easy to do. It's 8.8%. The next one down is 4.4%. And these are negative because I'm going down. This is minus 8.8% and minus 4.4%. How about the up 1 standard error and up 2 standard errors as a percent of the average? And it's just the standard error, 4.4 for 1 standard error up, and 8.8 2 standard errors up. This is a way to do these things without having to use the units of the average. Right? If this were millimeters or micrometers or whatever they measure ball bearings in, I have it as a percent of the average, and I don't have any units on it because I've divided the standard error, which has units, the same units as the average, by the average, and the units cancel out. if I go over to the other one, I'm going to get the same calculation, the standard error divided by the sample average. So this one is equals, there's the standard error, 2.44, divided by the average. And I'm going to make that a percent. %. Now I have a direct comparison in percentages. If I were doing ball bearings from another manufacturing facility, and I wanted to compare the results of this manufacturer versus this manufacturer, I can use the percent of the standard error as my comparison. Rather than directly measuring the distance in standard errors, I do it as a percent of the average. This one here, the 2.4, is a much better estimate, much safer bet, simply because of the sample size. Suppose I wanted to compare the ball bearings versus the length or the radius of tires. I go to Yokohama and I get the tire size, and I take that same size tire at another place that makes tires, and I can compare the size of those tires as a percent of the average. This is a way to do the estimates that is free of the units of the measurement. It doesn't matter whether I measure the ball bearings in inches, in millimeters. It comes out to be a percent and the units are gone. So here, for these, I've got plus and minus 4.4% of the true average with 68% odds. On the other one with the larger sample size, I got plus or minus 2.4% of the average with 68% odds. What's the bet on 95% odds? 2.4, one standard error. 4.8 is two standard errors. So if I repeat this calculation, over here, this one is minus 4.8. The next one is minus 2.4, 2.4 up, and 4.8 up. This is the same thing done a different way. Go to the next page. We're going to do this same calculation, and this is 100 samples. We're not going to use all 100. We're just going to use the first 25 because all we need is to show what's going on. So in this first spot, for this sample of size 10, the average was 100.7, and the standard deviation was 14. What's the standard error for this? Equals, there's the standard deviation. We're going to divide that by the square root of the sample size, which is 10. Going to knock some decimals off, but there is our 14 and 4.44. This is in whatever measurement units the average is, or the sample is in. If this is fish, the average length of fish is 100.7, call it centimeters. The measurements are in centimeters. The average is 100.7 centimeters. The standard deviation is 14 centimeters. And the standard error is 4.44 centimeters. So whatever the measurement units are, they're the same for the average, standard deviation, and standard error. And they have to be because I'm going to add and subtract them. So they have to be the same. Take this number and let's go for the first 25. Put the cursor on the edge box, the corner there, until you get a plus. Push the left mouse button down and drag it down to 25. Look at the standard deviations. If we're doing centimeters still, this is 14 centimeters, 18 centimeters, 10.2, 15.2. That's the bet on an individual. Standard errors are better than that. Go over to this -2 standard error column. And in there we want equals 100.7 minus 2 times the standard error. 91.8. Go to the -1 standard error column. And the calculation is equals 100.7 minus 1 times the standard error. No multiplication needed. Then we go 1 up equals the average plus the standard error and I'm going to make the columns smaller. They got big when all those decimals came out. Just adjust the width. And then do 2 standard errors equals 100.7 plus 2 times standard error. So there is 1 down, 2 down, 1 up, and 2 up. In these boxes next to it, we're going to put an X for whatever part of the interval actually contains 100. So for this one, 1 up, 1 down contains the actual average of 100. Then go to the 2 standard error column, and we want to copy that down to the 25. Do the same for the 1 standard error down. Same for the 2 standard errors down. And this is copying the formula, so it's doing the same calculation. Then look at the second one. The second sample, what interval contains the true average of 100? It's 1 up, 1 down. I'm going to put an X in there. The third one, the same thing. The 100 is contained in the 1 up, 1 down. How about the fourth one? Where is the 100? 2 down. It's less than 2 down. So it's outside of 2 down. The next one. Just go down the list, find where the average lies in that interval for that particular sample. Most of them should be in the middle. What percent of these intervals should contain the 100 in the 1 up and 1 down? 68. How many of them should contain the 100 in 2 up and 2 down? My only 2 bets that I need, 68 and 95. So if we go down here, here's number 7, and the 100 is in the upper end. It's not outside of the 2 up. It's between 1 up and 2 standard errors up. The next one is right in the middle. The next one is up 1. Next one's in the middle. Next one is between 1 up and 1 down, or 1 up and 2 up. Next one's in the middle. Next one's 1 up. Next one, I got 1, 2, 3, all in there. Next one, this one is in the middle again. Next one is on the far end below 2 down. Next one's in the middle where it belongs, or where my bet is best. Next one. And the last 2. Last 3. All of these are possible results out of the samples of size 10. How many did I get in the middle between 1 standard error up and 1 standard error down? Count the number of X's I've got there. 1, 2, 3, 4, 5, 6. I missed one. That's 7. 8. I missed another one. 9. 10. 11. 12. 13, 14, 15, 16, 17. 17 out of 25. 17 times 4, 40, plus 28. I got 68%. Pure dumb luck. It came out exactly what it was supposed to be. And it isn't going to do that very often. How many should I expect below 2 standard errors less than the mean? What's the percentage of the area to the left of 2 standard errors down? 2.5. So 2.5 out of 100, I've got 25. 1, 2. So I've got 4 times 2 is 8. So I actually have more on the low end than I would expect. All of this is a bet. How many should I have in here? Didn't get any. How many should we have gotten? It's always the same picture. Here's the middle, 0, 1 up, 2 up, 1 down, 2 down, 68, 95, this is 2.5, and 2.5 here. How many do I expect in each of these pieces? 13 and 1/2, 13 and 1/2. How many did I get? None. This is a long run bet. There's no way to know for sure what's going to come out. This is where the bets come in. I get to do one sample. Here I did 100, and we just looked at the first 25. And it came out perfect in one spot and completely blew out in the rest of them. So there's no way to know for fact what's going to happen. I did this for all 100. And these are the same things, and these are the actual number that came out of 100. So in the middle, between 1 down and 1 up, I got 67 out of 100, which is pretty close to the 68% I'm supposed to get, or the 68% that I'm betting on. Here, lower than 2 down, I got 4 out of 100. And I expect 2.5. Between 2 down and 1 down, I expect 13.5, and I got 12. On the other end, between 1 up and 2 up, I got 13. I got way more in the ends than I would expect. I expect 2.5%, and I got 4 out of 100 on each of those ends. All of this is pure bet. And here we've got 100. We get to do 1. We don't do 100. We get as many samples as we can from 1, and the rest of it is a bet. Over here is a sample of size 50. Do the same calculation for the 50 as we did for the 10. Standard error first. This is equals the standard error, 17.2, divided by the square root of 50. I'm going to copy that down for 25 or 20, whatever works. Then 2 standard errors down is going to be equals to the average. First one is 100.3 minus 2 times the standard error. Copy that down. Compare the standard errors between the 50 and the 100. 2.44 on that one, 4.44 there, 5.94, 1.93. That's the advantage of sample size. The standard deviation doesn't change very much. I can't affect it with sample size. I can only find out what it is. Back here, I'm going to do one standard error down equals the average from each sample minus the standard error. I'm going to copy that formula down, and I'm going to make the column smaller. This one equals the average plus one standard error. And then two standard errors up equals the average plus 2 times the standard error. Copy it down. And I can do the same thing with this one. The only difference between these two is how wide the interval is. How many or what percent should be between plus and minus 1 standard error up and down. Only two things you need. 2 and 1. 2 up, 2 down, 95%. 1 up, 1 down, 68%. Right? We have a whole calculation we can do to get any percentage for the normal distribution. But if you remember 2 and 1, you've got the two basic bets. And most people only make a 95% bet. They wouldn't do a 68% bet. They wouldn't think it was accurate enough. So make an X in each one that contains the actual 100 average. I should have the same percentage. The bet is still 68% between plus and minus 1 standard error. These are the bets. I only get one sample, and those are the bets I get to make. Also, these numbers came from a normal distribution. Original population was normal. If I don't have a normal distribution, I still have normal distribution bets. But they won't be as good until I get to larger sample sizes. The file with all of the answers on it is also in MyOpenMath, and it's that one there with results. So if you want to see what happens with all of them, you can go and look in that file.